All right. So in the previous class, we saw how to build a linear regression model, right? And the solution, I deliberately missed out a lot of points just to show you that what are the common issues that many people do. We make sure to check the assumptions, but we miss out on a lot other things. For example, we miss out on doing the outlier treatment. We miss out on the handling the column data types, right? Irregular values anyway we make sure to handle, because otherwise we'll get error. But wrong encoding is done. Feature scaling that is done is also incorrect. Okay. And we fail to check multicollinearity, cardinality. So all these things we fail to check. That is why we got very less scores, right? So last time when we did it, our scores were very poor. So we got only 68% after doing all the checks. We got only 68% of the, as you can see, accuracy scores on both training set and test set. Okay, so this is just the very how do I put it, new way of doing it, amateur way of doing linear regression. So let's look at the correct solution. But I was in the process of building this correct solution on the data set that we discussed previously, but I didn't get enough time. Like I said, I've been very busy this entire week, but I will show you the correct solution on the very similar data set, but all the steps will be same only. Okay, so same only, it's just that the features are differing a little bit. Okay, but otherwise all the steps exactly apply there also. I will anyway complete this notebook. I did it half, I believe. I did it half and then I have to stop anyway. So I will show you the solution in this data set. Now when you read the data set, okay, so the data set looks like this. Instead of Indian manufacturers, now we have a combination of Indian as well as foreign manufacturers, and you have sales in 1,000, number of sales, basically number of sales is in 1,000, year resale value, okay, for a particular year. So that is given. Vehicle type is same as what we had previously, and price in 1,000. Instead of selling price, we have price in $1,000. There we had in Indian rupees. Here we have US dollars. Engine size is common, horsepower is common. Again, wheelbase, width, length, these are additional ones. Again, curb weight is also given. So basically curb weight is the weight of the vehicle without fuel. Okay, so fuel capacity is given, fuel efficiency is given, again launch and perfect power factor. Okay, power performance factor basically. So that is also given. Features are varying a little bit, but otherwise the steps will be same. Okay, the first thing what we have to understand is when you are working on linear regression, okay, so these are the things mandatorily you have to check. First thing is check for missing values. After this, I would say check column data types. Okay, so first step, you can always, in any data set, you can always go for missing values. Okay, handling the missing values, and after you handle the missing values, you can check for column data types, irregular values, duplicate rows, and then you can come up with your own features if you want. Okay, and outlier treatment has to be done, encoding has to be done correctly. Again, out of all this, you have to ensure that which are the right feature selection has to be done, which are the right features that are going to be in the model, and then scaling also has to be done. I have also not added, apart from scaling, you also have to make sure of transformations. Okay, so these transformations you have to do mandatory for linear regression, especially. No escape on this. Okay, very, very important step. Otherwise the whole purpose of using linear regression fails. Where it fails, I'll show you. So transformations have to be done, scaling, and then you can build explainability if you want. You can make use of libraries like SHAP, Line, or linear regression also offers an inbuilt explainable features. Okay, actually they call it Shapley values, or you can also PDP. Okay, partial dependence plots we call it. Okay, partial dependence plots, and there are many others also. I will we'll talk about that when we talk about linear regression. Again, you will have to use better version of linear algorithm. Mainly you have something called lasso, ridge, elastic, and then there is a new one in the field, that is called Huber regression, and you have to also ensure that overfitting and underfitting is not happening. Okay, so these are the usual steps that you have to do for almost all the algorithm, but especially for algorithms that work basis on distance, okay, or basis on what we call it as linear decision boundary. Okay, I'll show you what decision boundary means and how that gets calculated. We'll talk about it. But wherever distance metric is used, okay, and I'll show you where exactly the distance is being calculated for linear regression. Okay, wherever distance is used, you have to ensure, okay, that a better version of these algorithms are being used and overfitting and underfitting are being handled. Okay, so pretty much let's get started. So the first thing is we want to handle the missing data. We want to first make sure what is the type of data available for us. As you can see, total is 157 records only, but out of that here in fuel efficiency 1 record is missing, and here in year sales couple of records are missing. And in order to understand, okay, in this data set what we have done is, first we have reversed these steps. Okay, ideal preference is to go for missing values first, but here we have switched these steps. Step 1 has become step 2, step 2 has become step 1. Okay, so either way, whichever way you handle, it's fine. Now if you look at the data types, first look at the data types. Manufacturer is an object. Now what is meant by manufacturer? If you look at, there is no order here. Manufacturer has no order. Okay, and hence we call it as nominal. Okay, nominal variable. See, there are mainly 4 types of variables: discrete, continuous, nominal, and ordinal. Right? So ordinal follows order, nominal does not follow order, and this you already know. Discrete means it's a normal numeric value. Continuous means also numeric, but it's mainly a float value. Okay, and here these are categorical categories with no order. These are categories with order. Okay, so I have already for these type of variables, I have already attached a reference in the same document. Okay, in the same notebook. At the end I have added a reference wherein which you can go through. So this is the reference what I have added. So for a variable that shows a single categorical column, okay, for example furniture or manufacturer, in our case it's manufacturer, where you have different manufacturers like Acura, you have BMW, Audi, etc., etc. So you have to, okay, go with one hot encoding. Okay, basically, if the categorical variable is nominal, that means there is no order. Okay, we usually go with one hot encoding. And if there is a variable where there is a order, for example, education level, as you can see, you have in our Indian education system, you have pre-LKG, right? Pre-KGs you have, then LKG, UKG, then you have primary school, secondary school, then you have graduate level, then you have postgraduate, then you have degrees, right? So all these have order. Now for order, you have to do label encoding. Okay, so likewise you have binary encoding also. Binary encoding is very similar to one hot encoding. This is also applied for nominal. Okay, nominal data only. Okay, just a different variation of it. You can just go through. And then target encoding. Target encoding is considers, it's also called as mean encoding. Basically, for your target, whatever you are trying to predict, and whatever you are trying to predict, if it is a category, okay, then you use target encoding. This is mainly used for classification. Okay, but in our case, we are doing regression. We are not doing classification. We are calculating the value, a numerical value. Hence, this does not apply to us. Okay, usually, and we also have frequency encoding. If something is repeated multiple times, okay, that type of encoding can also be done. Now, this is mainly done for when the data is, as you can see here, when the frequency of the categories is imbalanced. This technique should be used especially when the frequency, actually when there is a frequency in the categories. But if it is imbalanced, you have to be careful. Okay, mainly it is used in text. When you are working with text data, you can make use of frequency. If a word occurrence, if occurrence of a word is huge number of times, for example, if you are trying to parse a legal document and you see the word legal many times, how do you classify the document without knowing that it is a legal document? That is by frequency encoding. So if you see something is repeated multiple times, you can make use of this type of encoding and come up with something called n-grams. Okay, we have something called a technique called n-grams in NLP. We'll talk about that later, but I'm just giving you a small base kind of foundation. Okay, so there we also make use of frequency encoding. So these are the different types of encodings, okay, which you can consider. I have already attached link in the notebook at the bottom as a reference. You can go through. Okay, now basis on each and every type of variable, we have to ensure whether it is going to be a category or whether it is going to be an object. Okay, as you can see here already, for this manufacturer, it is saying as object, but manufacturer is nominal. It has no order. If it has no order, it has to be a category type. Okay, so that is why we are changing manufacturer to category. Are you following me? Is it making sense?
Yes.
Okay. The second thing is model. Again, the same story repeats here. Model is, first of all, does not have any order. Okay. Although there is some order for these models. If you consider only BMW, so then there could be some order. Okay. But if you consider overall model, then there is no order. There is no exact order. Okay, hence we are classifying it as category. But if you look at individual level, maybe Audi, okay, A4 is smaller car, A6 is bigger car, A8 is the biggest one. Okay, so that way there is order. But if you consider all the cars in one go, then there is no order at all. So hence we are considering that as category. Okay, and vehicle type also is a category, same way. Okay, vehicle type is whether it's a passenger or whether it is owned by any corporate. Okay, so that way vehicle is also category. Next is after changing, you can change something to category in a very simple way by making use of as category. Okay, if you want to change it to new int, you can just mention as type of int or as type of float or as type of category. Okay, with the exception for a date. If you want to change something into a date, okay, then there is a entirely different way of doing. You can't use as type. Okay, Python does not offer as time value to change a column into date, but you can change as type to making use of as type. You can change it to category, or you can change it to int or float. Okay, these three options only. Especially when it comes to date, you have to make use of one of these three. Okay, one of these five. Okay, so those five are, let's just say inserted date is a date format completely, year, month, date and all of that. If you want to extract only number, only year, you can make use of strf time. Okay, so this we have already discussed in the past, and you can also do that by making use of dt.year. Now dt being import date time, actually from date time import date time, that is called as dt here. Date time is dt here. Okay, so this way you can extract the date. Second way of extracting the date. Third way of extracting the date is if you want to set year as the index, then you can extract this. Okay, this is the third way. Fourth way is using 2.2 period. Okay, fifth way is by making use of apply lambda. The same thing here, same thing, but making use of apply lambda. Okay, fifth way. And then you have another way. If you want to set it, if you want to create a new column, another way is pd.to_date time. Okay, either you can use strf time directly on a column, or you can make use of pd.to_date time. So for date time there are multiple ways. You have to test which one works for you. Okay, so examples are given. I have attached this also as a reference for you, so that you can just get some basic idea on how to extract dates. So from here, as you can see, year is extracted. Here also you can see year is extracted. Here also year extracted. So multiple ways of doing the same thing basically. Okay, so you can go through this. I have attached in the notebook. So as type you have to remember, it's only for category, integer and float. Okay, we have handled three different columns, first two and another one. Okay, now what about the rest ones? For rest ones, if you go through carefully, everything is in proper format. Latest launch is object only. Okay, we can't have a category there for launch, but rest of the things, if you pay no attention, everything has been sorted correct only. So we don't have to do anything else. So this is the first step for our pre-processing. Okay, this is the first step in fixing the linear regression. Okay, second thing is handling the missing data. Now missing data, you can write a very simple code as well. Just you can say dataset dot is null dot sum. So if you do that, is NA. Okay, so either is NA or is null. So both are same only. So you can quickly see which column has particular column has missing values more or less. Another way of visualizing it is using missing number. Okay, missing number, you have to do pip install missing number, and in that you have a matrix option. You can pass your data frame. When you do this, you should be able to see this type of matrix, okay, plot. Now see here, you can only see which numbers are missing, okay. I mean, how many columns, how many rows are having missing values for each column. But here you can visualize at what level. I mean, usually if you imagine this as row numbers, as you can see here, they are already numbered, right? 1 to 157. At what row level you can get an idea they are missing, okay. So sometimes using this, okay, let me show this to the other one I was trying to apply. So if you can see here, immediately using this I can say mileage, engine, max power, torque and seats have missing values, and I can say there is a pattern there, okay. Immediately you can say, okay, whatever the data is missing for mileage is also missing for engine, is also missing for max power, is also missing for torque and seats. That means if I don't have data for 5 different columns for the same row, I can get rid of that row. I don't need that row, okay, because imputing 5 different columns for the same row, it doesn't make sense. If it was missing for one, maybe I can understand, I can do the imputation. But if it's missing for multiple, same row is missing for multiple columns, then better to get rid of it. No need to impute it, okay. So that is what I can see here. As you can see, lines are horizontal, so I have considered dropping this rows, okay. So this way you can make the call here as well for this data set. As you can see, this row, this particular row is missing for all the columns, so I will remove this without hesitating, okay. But for others ones, for this one, okay, for it's missing for only fuel efficiency, so I will impute it. I don't want to drop it, I will impute it, because I have rest of the data. Just because of one missing column, I can't lose the other ones, okay. This way you can make the decision. Again, handling missing values is not very straightforward, okay. It has its own way of there is a much more things for missing data than what is being seen here. And for that we have something called a chart here. As you can see, if you want to do single imputation, when it comes to imputation, okay, handling missing values, like I say, like this we have already discussed, that missing data is of 3 types: missing data at random, not missing data not at random, so MCAR, MNAR, MMAR, right? So this is what we have discussed: missing completely at random, missing at random, and missing not at random, okay. So for each one of those categories, so here you have missing data at random, so for each one of those categories you have to take the call accordingly. If the data is missing completely at random, okay, like what we saw in the matrix, it is missing for one row, it is missing at one column only, and there is no pattern, then you'll have to impute it, okay. So if it's missing for the entire row, then you can delete it, okay. So for each one of these cases there is a way of handling it, okay. How to delete it also, there is a specific way. You can just go through this article and get more idea on that, okay. So I have added this as well in the reference link. Please go through. If you want to have immediately in one go, you can just understand here. So for single imputation you can do mean, median. If it's numeric, you can do frequent value also, last observation also, carry forward also. Or if it's a dynamic, you can do various custom approaches. They followed their own approach, but you can do your own custom approach. And for categorical data, okay, if you want to impute, first of all, if you want to impute, we are not talking about deletion. So for multivariate single imputation, you can make use of k nearest neighbors, or now these days k means KNN imputation, k nearest neighbors is being used. excessively. Okay, and you have a lot of other ways of imputing. Mean imputation comes here. Okay, fine. And then for multiple imputations, if you want to do, you can follow joint modeling based approaches, basically modeling approaches. And in order to do these imputations also, you have a library. You don't have to write your own algorithm. There is a library called feature engine, where you have a lot of options. Okay, for imputations also you have a lot of options, so you can just have a quick look. Okay, maybe okay, so you can go through this feature engine. You can do a pip install and then just have a look. There are lots and lots of already built-in options into this. Even for missing data, they are there. Okay, so you can just refer. Again, I will anyway teach you this in depth because we will be doing feature engineering. But anyway, if you get time, just have a look at it. So this way we are doing the second step. So second step is, first step is we did the check on column data types. Second one is we are doing the missing values. Okay, so missing values, we are just analyze the missing values. Now whether to keep them, drop them, we will look at them later on. But two things we have identified. One we have fixed. Okay, now the third thing is, okay, looking at three different things. For the third thing, what you can do is, one, irregular values, duplicate rows, okay, and distributions, transformations, encodings, outliers. So all these things we have to see, but for now you have to look at each feature and what it looks like. Okay, what is its distribution? We have to understand that, whether it is skewed, whether it is normal. Now why we need to check whether it is normal or not? It's because linear regression is built on that assumption, normality. Okay, so the distribution should be normal, otherwise linear regression cannot be applied. If you apply, what will happen? This type of results you will get. So the results that we got, as you can see here, the Cook's distance was very high because of outliers. Here, as you can see, because of normality, our data errors or residuals were not aligning with that diagonal line, right? So these type of errors will come, and if someone deploys this model into production, the company which deploys will go in huge loss. Okay, so if loan approval system, if this model gets deployed into loan approval system, people who are not supposed to get loans will get loans, and people who are supposed to get loans will lose out on loans. Okay, such things will happen. So that's why these things have to be handled. Now coming back, so handling the distribution is important because that is the assumption, one of the assumption of linear regression, that the features should be normal. Okay, so we are looking at the value counts for manufacturer, because we know it's a value count, only we can check. So we are checking the value count, and if you look at the distribution, basically we are trying to analyze mean price. So this is additional thing that we are trying to do. Okay, but the main thing is the distribution. As you can see from the very distribution, there is no pattern only here. Okay, and what do we call such distributions? I am not sure if you remember. So we will discuss this in so there were multiple distributions, right? One is called Bernoulli distribution, uniform distribution, and then we had discrete. For discrete variables we had certain distributions. For continuous we had distributions, right? Okay, so this, whatever we saw just now for car sales, happens to be one of the example for uniform distribution. Ideally uniform has to be equal, but in our case it is not equal. Okay, and Bernoulli is for only two. two cases, either it has to be true case or a false case. Okay. So Bernoulli cannot be the distribution because we have multiple values here. We have multiple values. It can't be Bernoulli. Okay. So and then we also had Poisson distribution. Okay. So as you can see here, Poisson distribution is events should be independent. Again, event can occur any number of times. Two events can't take place simultaneously. It could be a Poisson also, right? So as you can see, we have discrete. We can't go for continuous values because we don't have continuous values. We have discrete values only. Discrete means numeric values, non-decimal values. So these are all non-decimal values now. If you can see, manufacturer. Okay, here it's not there. So manufacturer, as you can see, it is a count. Count cannot be decimal. Okay, these counts can't be decimal. So as you can see, this distribution is either a part of Poisson or uniform. Okay, little bit, although it's not exactly uniform, but yeah, could be a variation of uniform. Okay, so immediately you can tell what type of distribution it is, and this distribution will not work for our linear regression. Likewise, again, one more thing to notice, these are categorical variables. These are non-numerical, not numerical, categoricals. And for categorical variables, there is a different thing that we need to do. Anyway, I will show you what about for the transformation part. So this way we are just checking the distributions, how well our data is distributed. For vehicle type, as you can see, either it's a personal vehicle or I think passenger is maybe fleet. Okay, car means it's a personal vehicle, passenger means it's a fleet. So this way you can check, and for both of them you have done a simple group by and calculated the mean. Okay, and now we can tell which particular cars are selling for higher prices. Next is, we'll start looking for for categorical, this is what I was saying. For categorical variables, you can only look at the count. Okay, you can't look at the distribution, exact distribution. You can just look at how many times the values are repeated. Okay, hence we need not do any transformation. Very, very simple. This could be very well be a interview question. How do you transform the distribution of a categorical variable? The answer is you don't, because you can only look at the count. You can't look at the distribution itself. Okay, but for numerical variables, you can look at the distribution, how well the data is, the actual values are distributed, not the count of value. We are not counting how many times the car has been sold for 5 lakh rupees, but we are looking at the 5 lakh rupees only. We are not looking at how many times 5 lakh rupees has been sold, but rather 5 lakh only. Hence we can look at the distribution. Okay, so this distribution looks skewed only because most of the data is in the very beginning. If you see 0, but the actual values are at 600. Okay, so this clearly could be a outlier here, but as you can see, the data is skewed. Hence, if you calculate the skewness for this, it will come as you can see here, 3.41. Okay, skewness has been calculated already, so it is 3.41. So that we have to check for each and every variable. These distributions cannot be passed for the linear regression algorithm. Again, for skewness, if you check 2.29, it is left skewed. We call it left skewed, no?
Yes.
Yeah, left skewed distribution. This is also left skewed 1.77. Left skewed is also called as positive skewness. Okay, right skewed is also called as negative skewness. You can tell that just by looking at the value. It's a positive value, as simple as that. Okay, again for engine also you can see there is a little bit of skewness, but it is coming nearer to 1. So this distribution is still fine for us. Okay, anything that is closer to 1 is a good feature. Okay, so this looks little skewed, but if it was little here towards little bit slightly to the right, then it would have been a normal distribution. So this also, this is 1. See this is 1. This is good. This feature we need not touch. Okay, horsepower. Next is wheelbase. Wheelbase is also good enough for us, 0.97. Width is 0.48. Okay, so this also has to be handled. Again, this is, now this one is going towards right, hence it is negative. Right skewness is same, also called as negative skewness, hence is going to the negative part. As you can see, this way you can calculate all the skewness, and once you calculate, see what we are trying to do is, we are trying to understand missing values that we saw from the matrix. Second thing is, we are looking at the data transformation. Okay, so which features need the transformation. We also want to detect the outliers. That is what we are gonna do. Now, we already have discussed this. Outliers, the two most famous methods are IQR method
and can you just explain what is exactly included in the transformation? For example, we need a transformation somewhere, right here.
Yes,
then
yes.
what would be the steps? I mean, what we exactly do in the transformation?
Yeah, that is what we are. I was about to talk about. But first, I was listing out all the steps. Okay. Once you list out all the steps, then we were going to apply. See, transformation is nothing but you're going to do some sort of multiplication or division to that already existing values to make them look like a normal distribution. Okay. For that, we have something called as for transformations, we have multiple transformations. Okay. One moment. Mainly log transformation, power transformation, Box-Cox transformation. Okay. Let me open all the list. Okay. So the thing is, for a distribution, well, first of all, what is a distribution? Distribution is nothing but all the combination of all the values that are present in the feature, that are present in the column. Okay, it could be 1 lakh, car sold for 20,000, 1 lakh, 5 lakh, 10 lakh. Okay, and they represent a certain distribution. Okay, now what we are saying is, we want to, if you calculate for that kind of distribution, if you calculate the variance and standard deviation, mean will be somewhere, okay, median will be somewhere, and standard deviation will be some other value, right? Standard deviation is how far away your mean is, how far away your any data point is away from the mean. Okay, either in a positive or either in a left direction or in a right direction, how far away, that is the standard deviation. Now, such distributions cannot be used in linear regression. So what do we do in that case? A very simple thing is, we shift those values, we modify the values in such a way that they don't essentially lose out on the variance, on the way how the values are distributed, but their mean gets shifted, their median gets shifted. Okay, and how do we do that? Very simple. Either we do a multiplication, or we do a division, or we do a reciprocal, okay, or we do a square root of them. And when we do all of these, automatically the values shift, either to the right or to the left they shift. Okay, that process of division or multiplication or whatever with certain value, we call it as transformation. Okay, in this case, as you can see, there are multiple transformations. Log transform means, okay, what you're doing is you're just multiplying with log, you're just doing the log of all the values of all the rows. Okay, for that, so
it will be applicable for all the columns or a particular column, or depending on the requirement?
for each column, based on the skewness and based on the distribution, we have to take a call whether to go with the log transform or whether to go with the power transform, whether to go with the square root or whether to go with the reciprocal. That way depends on the distribution. Okay, now for positive distribution, for left skewed distribution, we make use of mostly we make use of something called as power transformers. Okay, and we make use of box Cox. Okay, if it's positive skewness, use box Cox, and if it's negative skewness, you use Johnson. Okay, now how it works is it just simply applies these values. Okay, applies logarithm, or it multiplies these. I mean, x is you already know. X you already know the row value, maybe 20,000, 50,000, 1 lakh for which the car was sold. It applies the natural logarithm over that value. Okay, or if the lambda is not equal to 0, okay, then it does this, x to the power of lambda minus 1 by lambda. Okay, now lambda is the power applied to each observation. Okay, how much power to apply, that depends on the algorithm only. And usually after this transformation is done, you will get the values between 5 to minus 5. Okay, so this is the way, this is how the box Cox transformation works. Or simplest thing, if you don't or if you are not satisfied with the transformation, then what you can do is you can try with box Cox first. If that doesn't work, you can try with some other transformation, square transformation or some other log transformation. Also you can try. So it's kind of experimental also. Okay, although there is best practices kind of things, but you are free to apply multiple transformations and test which one is working fine. Okay, so that way also you can do. So there are some best practices here, like I said, key takeaways or whatever the best habits that data scientists follow. As you can see, if you read this, it gets applied when 0 or negative values are present mostly. Okay, box Cox transformation is applied only to positive values, and you get the values after transformation, you get the values between minus 5 to 5. Okay, and you can come up with your own custom data transformations also. And log transformation works fine on the right skewed data, whereas square root transformations perform well on the left skewed data. Okay, this is you can just remember, log transformation is for right skewed data. Negative, if you have negative skewness, right means negative, left means positive. Okay, so log transformation works on negative skewness, whereas square root works fine on the positive skewness. If the value of skewness is more than 1, you can just apply square root, or you can try with box Cox also. Okay, and if you have negative values in your data, then you can apply Johnson also. So this way there are some best practices that you can do. Okay, I hope I'm clear.
Yes, got it.
Okay, all right. So basically, see here, I'll give you one simple idea. Let's just say 0 to 600 values are present here, in that too in sales in thousands. Let's just say you have a car that got sold only 50 times here, somewhere here. If you want to shift this point to here so that this distribution comes like this, what will you do? Very, very simple. You'll do the multiplication. Correct? You will multiply 50 to 6 times so that it comes at 100 and the distribution becomes like this. Now you will do the same process for all these values that are present. You can't apply transformation for only one row. You have to apply it for all the rows. Now what will happen? Each of these values will start shifting towards right. When it starts shifting towards right, your distribution comes in the center. Now it became normal distribution. Now when it became normal distribution, mean is at the center, median is at the center, standard deviation is at 0. When mean and median are at the center, standard deviation becomes 0. That is our aim. You can apply this, you can use only such features for linear regression. That is the assumption of this linear regression. Okay. So that is why we will do the transformation. Understood?
Yes, yes.
Okay. Likewise, let's look at right skewed. Okay, negative. So this is negative skewness. I mean, it's not highly negative, not very much negative, but let's just say, let me see if I can find some negative. There was one, right? I think there was one. Okay. Anyway, so if there is something towards the right, very, very simple. If there is if the skewness is on the right, distribution is on the right, what will you do to bring it to the left? You will divide, or you will apply some type of log, or you will apply reciprocal, or you will do something that decreases its value is what your aim is. Okay, something that brings it to the center. That is what you will do, transformation. Okay, after you do the transformation, it's so, I mean, mathematics is so beautiful that if you divide a bunch of numbers by certain value, their plot on the, when you plot them, they represent the same pattern. They have the same pattern. Okay. What I'm trying to say is, let's just say you have certain data points. Okay. And their distribution is in a way that, okay, let me quickly show you. So let's just say you have this plot, you have these points. Now what I'm saying is, if these are on 100 scale, 0 to 100 scale, okay, if you divide this by 50, each and every value, if you divide by 50, what happens is, they will exhibit the same exact pattern. Now I can't draw the same exact point, but I'll try. So they will exhibit the same exact pattern without changing the values. The only thing that will change is 0 to 2, because you divided by 50. The pattern remains the same. Okay, pattern will remain the same. There is not essentially much change. Okay, so the distance between these two data points decreased by a factor of 50, but nevertheless, if you want to calculate certain metrics on top of them, it will remain the same. Hence, if we do the transformation, our algorithm will work exactly the same way when the data would have been in its original form, but in that same distribution. Did I make sense? Did you understand?
Yes, yes, got it.
Okay, all right. So that's why doing transformation does not make much
The
difference.
same way like we scale the values, no?
Yes, yes. Same thing. So this is the third thing we are checking. We are checking for skewness as well as we are checking for distributions. Okay. Next thing is we'll handle the outliers. Outlier means IQR method we are using. Now IQR method is also called as two-way method. Okay, just I mean, need not remember, but just for your information only. So we are just checking IQR. We are already seen. 25th percentile will calculate, 75th percentile will calculate, will take the difference, and then that difference is multiplied by 1.5 times. Now this is just the, how do I put it again, this is what statisticians generally believe. This is not always true, but the general way of detecting outliers is this. Generally, when you have a normal distribution, and again another interview question is, you can't apply IQR on a non-normal distribution, non-Gaussian distribution. You can't apply. Why? Because standard deviation is different there. Okay, so
can I ask? Hello,
Yeah,
am I
yeah,
audible?
yeah, please.
Uh, so then what is the difference in the scalars and the power, let's say we are,
Hmm.
transforming. So
Okay.
is a scalar a kind of transformer only? Scale, in,
Scaling, you mean?
yes, yes. Because we, just now we were talking about, you were talking about that, uh, there is, whenever we are actually multiplying or dividing by something, so we
Hmm.
can generally call it as a scaling. So, is there any difference in the scalar and the or scaling and the transformation, the
See,
process
the
of
thing
scaling?
is, yeah, yeah, there is. Very, very simple. Okay. Again, you'll have to understand this from a point of matrix multiplication. Okay. See, let's just say transformation. What transformation is doing is it is shifting the values. It is shifting the values to the center so that the values come to the center. But not always this scale that you see. Earlier it is 0 to 200. After shifting it little bit to the center, the scale may remain same, 0 to 200 only sometimes. Okay. So in this case, if you see this distribution, if I multiply it by 1.1, let's just say, this will shift little bit to the right, and it will the scale will remain the same, 0 to 200. Okay. So that means the value, starting value will still remain as 0. The ending value maybe it will go to 200 or 210, 220, because I multiplied by small difference. Okay. So this is transformation. We are transforming only the distribution. But that is not what scaling is. Scaling, again, in scaling there are two different techniques: standardization and normalization. Okay. Now feature scaling means either standardization or normalization. Now in scaling, what is happening instead is we are decreasing the scale. We are bringing it closer to 0 to 1 or -1 to 1. Why? The question is why? Why do we need to do that? Simply because you know that linear regression means is just a matrix multiplication, right? When you are multiplying the number, so see, if you multiply 1 million into 75,000 something, you'll get very big number. That's a big computation. Okay, you have to think in terms of processor now. Multiple gates have to be fired in order to do that multiplication, correct? Big numbers means more memory has to be stored for bigger numbers. Okay. Instead, if we don't lose out on the value, if we don't lose out on the pattern, if we decrease the scale 0 to 200 to between 0 to 1, okay, just like how I showed here, okay, just like how I showed here. Now this value could be 0 point something, 0 point, let's just say 0.2 for the sake of argument. Now multiplying 0.2 with 0.4 is much simpler than multiplying some millions of numbers into some other higher values. So
Got it. Yes, yes.
decreasing this scale is called feature scaling. Okay.
Okay.
Transforming is transformation is different. Transformation is we want the distribution to be normal. That is our aim. Okay, this way the distribution should be. But here that is not the case. Here the case
Got it.
is to decrease the scale. Feature
Sure.
scaling is different. Yeah. Again, we'll
Right.
talk about feature scaling also. There are two different techniques there. We'll talk about that. So anyway, so once you handle the, okay, for outliers, what we are doing is we are applying the IQR method and getting rid of any values that do not fall under this region. Now, why do we need to get rid of outliers? Simply because we saw here, what did outliers do? They increase the residual distance, Cook's distance that we discussed previously. Okay, when this residual distance is huge from this starting point of these dots, notice how far away these dots are. So when leverage increases, okay, your model suffers. It is no longer a good fit model. Okay, it no longer does the correct prediction. Okay, that is one. Second thing is outliers. Outliers also increase this mean squared error. Look at the mean squared error, or look at the mean absolute error in the selling price. So that means for every car, if we went ahead with this model, then what we are saying is for every car that you sold, okay, you will incur a loss of 2,70,000. Okay, because that's how far away your price is from the mean selling price. Okay, mean selling price, either you're incurring a loss or customer is incurring a loss. This is no longer a generalized price. Okay, so mean squared error increased, mean absolute error increased, root mean squared error increased. Even the best fitness is only 68%. That means your model is able to understand and correctly predict 68% of data only. Rest 32 is gone. Okay, so even the MAPE factor is mean absolute percentage error. 74% it is doing correctly. Rest 26% it's not doing correctly. So this way, outlier has direct impact on your residuals. We call them residuals, right? So residuals is the difference between y-test and predicted value and the actual value. So that takes a hit. That's why you have to get rid of these outliers. Okay, if you yeah, and missing values are also we are handling. Missing values we already saw above. I will skip this part. Next is there are certain columns which we don't need. For example, manufacturer. What will I do by knowing manufacturer? Nothing. Okay, manufacturer may not be much useful for me. Likewise, model. What will I do by knowing the model? Certain columns can be straight away. Even the launch price or whatever, latest launch or whatever. So that also may not be of much use to me. But from the launch year, I can derive how much is the age of the car. So this is where your intelligence, your cleverness will come in handy. Whether to go with the existing features or whether to derive new features is something subjective to each data scientist. Okay, and you have to think it through very clearly. So manufacturer here, as you can see, we have retained. Okay, anyway, the point is I'm trying to show age. Yeah, so age you can calculate from the current year. You can subtract the launch date of the vehicle, and this may be helpful feature. We will see. We'll get to know whether if it is helpful or not in the correlation when we calculate the correlation. Another one is after we calculated the age, we have to again look at the another mistake done by data scientists is they'll check the distributions for all the existing features, then they'll derive new features and then fail to check the distribution for the new features. That should not be the case. You have to check the distribution for this also, and skewness also 1.59. This also has to be handled. This also has to be Cox transform, or some transformation has to be done. Okay, so next we are applying the transformation. We are going with Cox transformation in this case, but like we have already seen, you are free to experiment with your own way. There are multiple transformations. If you just Google, you will get to know lots and lots of transformations are available. The only aim for you is to decrease the skewness. Skewness should be closer to 1, and when you plot it, it should look like a normal distribution. That is the aim of these transformations. It doesn't matter which transformer you are trying to apply, but the aim is to decrease the skewness. That you can remember. Once you apply the skewness, look at the skewness decrease, the now you can see the distribution is looking like a normal one. Likewise, if you see the same thing for other one, before transformation, skewness was 2 points, now it is closer to 0, looking like normal distribution. Okay, so this way you can apply the transformation. Again, it should not be the case that you apply the same transformer to all the features. You can apply different transformers to different features. Okay, no need to follow the method that is shown here. You can experiment with different transformers. Next, once you handle the transformers, once you handle the distributions, the next step is to normalizing. This is what your question was. Feature scaling is the question. This point, scaling part. Now, scaling part is of two types. One is called as normalization, and another one is called as standardization. Now, normalization means, let me open. See, normalization means what you are doing is, see, like we already saw in this thing, you're just trying to decrease the scale so that matrix multiplication happens very easily. Okay, so there are two ways to do that. One is called as normalization. Normalizing. What is meant by normal? Normal means something that is distribution is looking at the center. Okay, I mean the mean, median are at the center for a normal. Now, feature scaling, okay, feature scaling, although we are trying to decrease the scale, it also sometimes does the task of distribution. It may change the distribution slightly, not much, but slightly. Okay. So, normalization is also called as min-max scaling. Why? Because the way how you do the transformation here is, the feature scaling is, you take that 5 lakh rupees for which you sold the car, and then you look at the minimum value. Let's just say there was one car which was sold for 1 lakh rupees. Now you'll do that 5 lakh minus 1 lakh divided by, let's just say there was a car that was sold for 20 lakh. 20 lakh minus 1 lakh. That is 5 lakh minus 1 lakh, 20 lakh minus 1 lakh. So that is minimum value divided by max value minus minimum value you will do. So this way, what will happen is, now what happened? Earlier, there were outliers somewhere here. The scale was in some 20 lakhs or 30 lakhs or whatever. Now, because you chose the max value in the denominator, max minus 1, the scale automatically fell down to, all these outliers were gone now. Okay, all these values got shifted to this side. Okay, and these values moved to left side. Okay, these values moved to left side. These values came here. Now, instead of 30 lakhs, you have 30 minus 1. Okay, or 20 minus 1. 19 lakhs you have here. Okay. Okay. But this is only the denominator. You also have to take into account numerator. In numerator, what happened? 5 lakh minus 1 lakh became 4 lakh. Now 4 lakh is in numerator, 19 lakh is in the denominator. 4 divided by 9 became very less value, no? Very small value. You can do the math. 19 ones are 19 twos are 32, 2 point something. Okay, I don't want to go further. 2 point roughly 2.1 something.
0.2.
Now, sorry?
0.2.
2.2?
No, 0.2.
0.2. I'm sorry. Yeah. No, I shifted, kind of assume 0. Yeah, correct. You're right. So that means not 2.1, it's 0.21. Okay. Now this became 0.21. Okay. This entire, the entire scale became between 0 and 1. It came between 0 and 1. Okay.
Basically, the range is shifting between 0 to 1 or minus 1 to 1, something like
correct.
that.
Correct. Yeah. So this scale changed from 0 to 1, or sometimes if you have smaller values, it will become minus 1 to 1. Okay. So this is one way of changing the scale. without altering the actual distribution. Second way is standardization. We also call it as Z-score normalization. Now here what we do is, we are essentially calculating how far away the points are from the mean. So we are just subtracting the mean divided by standard deviation. Okay, when you do this, the values again fall under the same range. They also come under the same range. But this has to be used, standardization has to be used when your feature is normalized, which is what is in our case. We have transformed these features already so that they look like a normal distributions. Hence, we have to apply the better way to apply is to go with the standardization. Okay, so we can use this. But if you don't know the distribution, if you are confused which distribution it looks like, then you can do for certain algorithms like tree-based algorithm, we don't care about distributions. We don't do Cox transformation, log transformation, all those transformations we don't do. In that case, you can directly go with normalization. Okay, if you want to do the feature scaling. But in this case, linear regression, we want normal distribution. You can do the standardization procedure. Either way, whichever you want to try, you can try. And in scikit-learn, you have to do standardization using standard scaler. Using normalization, you have to do using min-max scaler. Okay, so I will include this link. You can go through. Next is, okay, fine. We will stop till here because we are kind of extended the class.